confidence interval for the mean using the t-distribution. Example 1, in a sample of n equal 21 sedentary people, the mean glucose level x bar 5.2 milligrams per deciliter with a standard deviation s equal to 0.4 milligrams per deciliter. This sample is taken from a larger population of the entire population of sedentary people, and we're assuming that's normally distributed with unknown mean mu and standard deviation sigma. Part A, find a 95% confidence interval for the unknown population mean. That means 1 minus alpha is 0.95, that's our level of confidence. Alpha itself is 0.05, that's our level of doubt or level of significance. First step, look in row n minus 1, 21 minus 1, which is 20, in the t-table, and column 0.025, that's alpha over 2 is 0.025, and to get our critical value from the t-table of 2.086. Next step, the lower bound, x bar, the sample mean minus the t-score times the sample standard deviation divided by square root of n. So just plug in the numbers. 5.2 minus 2.086 times 0.4 divided by square root of 21. I'm computing the part after the minus sign separately because sometimes it's useful to report that number by itself. That's called the margin of error. The 2.086 times 0.4 divided by square root of 21 comes out to be 0.182 something. And then if we subtract, we get approximately 5.02 milligram per deciliter. The upper bound, it's the same numbers except you want to add the margin of error, and that comes out to be 5.38 milligram per deciliter. So that means we are 95% confident that the mean glucose level in the entire sedentary population is between 5.02 and 5.38 milligrams per deciliter. Part B reports margin of error, as we mentioned before, that's approximately 0.18 milligrams per deciliter. To use these formulas, some texts require either sample size n of at least 30 or that the variable is normal, but ours does not require that. Our text does not require that. Part C, we can also find a confidence interval for the variance. The sample variance follows what's called a chi-square distribution, which is not symmetric. So we have to look up two separate numbers in the chi-square table. So the we want the our desired confidence level 95%. That would be the middle part, and our doubt is going to be on either side, and we'll have an upper critical value and a lower critical value from the table. Using the chi-square table, we want to look in row n minus 1, which is row 20. 21 minus 1 is 20, and 1 minus alpha over 2 is going to be 0.975, and that the number from the table is 9.591. And then if you look in row n minus 1, column alpha over 2, it's row 20, column 0.025. That's the value there from the table is 34.170. So the lower bound, this is what we're going to use for the lower bound. It's n minus 1 s squared over the upper critical value from the table here. 20 times 0.4 squared over 34.17 comes out to be about 0.093. And then the upper bound is going to divide by the 9.591 to get 0.333. So that means we are 95% confident that the variance of the glucose level in this entire sedentary population is between 0.0936 something and 0.333 something. We can also take the square roots of these to get a confidence interval for the standard deviation. Square root of the lower bound is approximately 0.31. Square root of the upper bound approximately 0.58. So that means we are 95% confident that the standard deviation of glucose level in the entire sedentary population is between 0.31 and 0.58 milligrams per deciliter. And just to note, the confidence interval formula for standard deviation and variance require that the sample be from a normal random variable. And that concludes this presentation.